Okay, so we looked at organic parts where we talk about photosynthesis, respiration, decomposition. Of course, it had sedimentary rocks as well. Now let's look, just for completion, just the inorganic part, starting again with the atmospheric reservoir of 760 petagram carbon with silicate weathering, removing 0.03. Obviously, this is more resistant to weathering, as we saw with the granite and the limestone tombstones. Carbonate weathering is several times that, 0.17, so almost 6 times as much. They are obviously joining the pool of bicarbonate and carbonate, which is fairly big. Remember, HCO3 minus is 37,000 and carbonate is only 1300. You have precipitation of calcium carbonate and marine carbonate sediments being dissolved back into the carbon pool in the water. So that's bicarbonate carbonate pool. That leaves you with marine carbonate sediment pool that we had looked at before of 2500 petagrams. You have carbonate sedimentary rocks, 40 million petagrams. Carbonate weathering happening there. So carbonate weathering here, carbonate weathering there, both joining this pool. And the marine carbonate sediments, there is a sedimentation and burial rate estimated at 0.2 petagrams carbon per year. And there has to be a chemical equilibration between oceanic H2CO3 and carbonate and bicarbonate, right? Because that's how the reaction is buffering against saturating with CO2. So that's 740 petagrams, and this is a massive pool. So that's directly dissolving atmospheric CO2 and producing carbonic acid. On episodic events, you have volcanic eruptions of about 0.03. These are estimates, right? Nonetheless, the order of magnitude is very important. Again, you can divide the reservoir size by the fluxes to get estimates of residence times in each reservoir or each pool. Okay, this is the inorganic part. The main thing to notice is that the weathering timescales are geologic timescales. But with global warming, with increased CO2 and precipitation changes, you obviously can alter the weathering rates. And in geoengineering, we talked about doing artificial weathering as well. You grind up the rocks and you distribute them on soils, and it's easier to weather them when they're ground up rather than a huge block of rock slowly weathering because of the acid rain, okay, CO2 dissolved rain. Okay, so net removal of CO2 then is critical, right? So we talked about carbonate weathering going from calcium carbonate, limestones, marble, etc., plus H2CO3 producing calcium ions, which are, we said, pretty abundant in the ocean, and bicarbonate. Carbonate precipitation is basically the reverse of this. So on land, weathering is happening on land, right? And all that is washing into the ocean through rivers and groundwater, let's say. Okay. Carbonate precipitation is happening in the ocean, which means species that need to build carbonate shells like corals and coccolithophorids have to precipitate calcium carbonate out of the water. What does that mean? They have to be able to take calcium ions that are available and combine with bicarbonates and produce calcium carbonate for themselves, and then synthesize it into a shell. This is called calcium carbonate precipitation. So what's happening here? The net result that weathering is taking down carbon dioxide because it's in H2CO3. H2CO3 is basically H2O plus CO2, right? So you can write this as CaCO3 plus H2O plus CO2. So one CO2 is taken out, brought into the ocean as bicarbonate. But when carbonate shell forming species precipitate calcium carbonate out of the water, they are releasing that CO2 back, because H2CO3 is basically H2O plus CO2. So the net result of calcium carbonate weathering is that there is no net removal of carbon dioxide. There is no escape of the carbon dioxide molecule. Whereas silicate weathering, as we saw, is taking 2 moles of, I'm saying molecules, moles, you know what I mean, carbonic acid, producing calcium ions, 2 bicarbonate ions, plus silica, plus H2O. And carbonate precipitation out of that is going to really release 1 CO2 as H2CO3. But you have taken up 2, so you have sequestering, you are essentially sequestering 1 CO2. So when you do silicate weathering, you are essentially sequestering 1 CO2 mole as solid precipitation of calcium carbonate, as opposed to calcium carbonate weathering. This is the big difference. So in the long term, unless this CO2 is put back in, the weathering, remember this, the weathering rate is 0.03 petagrams carbon per year, but over long term that can still draw down CO2 out of the atmosphere if it keeps sequestering that CO2 into the ocean, right? So you need a feedback. You need to bring that CO2 back for long-term equilibration. That's always the case. In the long term, everything has to balance out. So that's how you get the so-called carbonate silicate geochemical cycle. So calcite plus silica in the system at the bottom reproduce the wollastonite that was getting weathered and coming into the ocean as calcium and bicarbonate and silica. And that's going to re-release the CO2 that was sequestered by the silicate weathering. So mid-ocean ridges release the CO2 that is brought down by weathering of silicate wollastonite, silicate rocks. When rocks get formed or sediments receive calcium carbonate and it is subducted under the continental plates or 2 continental plates meeting and volcanic activity. So essentially all that is going into the mantle where it's hot plastic, remember, it's going to be ground up, metamorphized and so on, and through the regular volcanic mechanism it can be put back into the surface, into the atmosphere. So volcanoes are putting back things on geologic timescales as well. Okay, so this is the coupling between silicate weathering on land, calcium carbonate precipitation in the ocean, and the carbonate silicate geochemical cycle from the bottom of the ocean back into the continental crust or volcanoes, exposed rocks, and so on and so forth. So that's a very long-term balance, which is important nonetheless. So long-term feedbacks are that if you increase rainfall, you're going to increase the rate of weathering. Okay, that's a positive feedback. If you increase the rate of weathering, you're going to reduce the CO2, so that's a negative feedback. If you reduce CO2, you're going to reduce the greenhouse effect, so they're going in the same direction. Coupling, not feedback. That's a positive coupling. All these are couplings, right? If you reduce the greenhouse effect, it's coupled to the surface temperature. The surface temperature is going to go down, so that's positive coupling. And if temperature reduces, rainfall reduces. Remember, if there is warming, there is evaporation, and evaporated water has to fall back towards, so there is a balance. If you warm and you increase evaporation, you're increasing rainfall. So that's a positive coupling as well. So there are 2 loops here. This is all positive, and this is 2 positives, 1 negative. It's a negative. So net feedback is negative. So it's the long-term stabilizing loop of carbonate silicate weathering, sequestration, and re-release of CO2. It's important to kind of go through these things just so that you know that there is a short-term organic inorganic carbon cycle, there's long-term organic inorganic carbon cycles, and they are coupled, and there has to be an equilibrium on long time scales.